Good evening, ladies and gentlemen, colleagues, students, and honoured guests. Welcome to Abertay University and to Professor Ashok Adya's Professorial Lecture. Professor Adya has had a highly distinguished career so far. He has over 130 publications to his name, many of which have resulted from interdisciplinary work covering a range of disciplines including chemistry, physics, biology, computing, engineering, life and forensic sciences. Professor Adya began his academic career as a student at the Punjab University, from where he simultaneously attained 2 undergraduate degrees, a BSc in chemistry, physics and mathematics, as well as an honours degree in mathematics. He then went on to receive his MSc in chemistry from the Punjab Agricultural University, where he is now an honorary adjunct professor. After his MSc, Professor Adya moved to Delhi, where he gained his PhD from Delhi University. He was awarded various research fellowships during his studies there, including a postdoctoral position, while still in the pre-doctoral stages of his PhD. Upon award of his doctorate, Professor Adya took up position of lecturer at Kirori Mal College, part of Delhi University, where he was subsequently promoted to the position of reader before going to Tokyo Institute of Technology to pursue his postdoctoral studies under the sponsorship of UNESCO. He then came to the UK to work as a research associate and then a research fellow at Bristol University, positions funded by the EPSRC, before being appointed in 1993 as a lecturer in chemistry at the then Dundee Institute of Technology, shortly before it became Abertay University. Professor Adya was promoted to the position of reader at Abertay in the year 2000 and became Professor of Nanotechnology in 2011. As well as his current position, Professor Adya has held visiting professorships in France, the Ukraine, Japan, and India, and continues to carry out research at international facilities in collaboration with many international partners. Professor Adya uses nanotechnology to investigate aspects and mechanisms of growth, metabolism, and the effects of a variety of environmental stresses on a diverse range of cells of industrial, environmental, medical, and forensic significance. This research involves applying nanotools to fields as diverse as biotechnology, food, forensics, and the material and life sciences. This evening, Professor Adya will present his inaugural lecture entitled The Nanotechnology Revolution, A Game-changer of the Millennium.
Good evening, ladies and gentlemen. Thank you for a very nice turnout, I see, and thank you for coming. I can't wait to hear the speaker just like you. So let's get going. Please feel comfortable in your seats and squeeze yourself to nanoscale before I take you down the nano lane to this wonderland of atoms and molecules. The title of this talk, as you've seen, is Nanotechnology Revolution. Nanotechnology revolution is similar to industrial revolution that we had more than 300 years ago, when we changed from wood to coal. We could not dig out water, we could not go deeper to find more coal, and from horses, the steam engine was discovered. So necessity is the mother of invention. And steam engine was discovered, Carnot cycle was discovered in thermodynamics, and so on. So this is the revolution, like plastics, computers, internet. Now is the time for nanotechnology. And that's what we are seeing in our daily life. What is nanotechnology? Involves harnessing of unique properties which exist at that scale, properties of nanoscale, substances in fundamentally new and unique ways, as you will see as we go along. Nanotechnology, the word nano means dwarf, combines different sciences, physics, chemistry, biology, engineering, material sciences, computing, and explores their intrinsic properties in a complementary way. Molecular machinery found in living systems dictates to us to find out some complex artificial molecular machinery so that we can mimic. It is like biomimics, so that we copy what nature does for us. We can copy the same things on a nanoscale. That is what is nanotechnology. Professor Richard Feynman from Caltech in 1959, he gave a very stunning lecture. The title of the talk was "There is Plenty of Room at the Bottom." What he wanted was, that time, the nanotechnology word didn't exist. He wanted to write 24 volumes of Encyclopaedia Britannica on the tip of a pen. People thought he was crazy. But he had the vision. And he said the principle of physics, as far as I know, do not speak against moving atoms and molecules and constructing new things on that level. That was his vision. And that means maneuvering things or controlling things atom by atom, molecule by molecule. In other words, there is a chemical synthesis we carry out by moving atoms and molecules. We, so to say, synthetic chemistry we do. In other words, we do chemical synthesis by mechanical manipulation to create new things, new objects, new machinery. And that is what nanotechnology is. World has always been around us. It is only now that we have started to explore this world. Effect of things have been happening all around us at a nanoscale. 4 billion years the life has been in existence, and it has taken us 4 billion years to understand this nanoscale, nanoscopic objects. So, welcome to the nano world. It's about 6:30. This morning I shaved it to get ready for this evening, 7:30. Nearly 11 hours times 60 minutes times 60 seconds. Beard grows at the rate of 5 nanometers per second. If you work it out, it comes to about 19,800 nanometers. So nearly 20,000 my beard has grown since this morning. Can you see it? No. That is what is nanoscale. 20,000 nanometers my beard has grown. So we live in that world. That is the scale of things we are talking about. That if a nanoparticle was the size of a football, a domestic chicken, I have put some bulletproof jacket for the forensic scientists who are in the audience. They will love it. So very, very small indeed. So it will be the size of the world. What is nanometer? How small it is? We use tools thanks to the discovery of all these new techniques without which nanotechnology would not exist today. For example, all those scanning probe microscopic techniques, scanning tunneling microscopy, it was discovered only in 1986. And initially, for first 10 years, for a decade, it was used for material sciences to investigate metals, alloys, conductors. People did not use it for biological sciences. It is only in 1990 that people started using it for biological applications, life sciences applications. So initial 10 years. So this is completely new, and the way things have changed during this time. For example, if you take a cell in your body, they are in every cell in our body, animals' body, plants' bodies, plant cells, animal cells. They are so tiny, only a few nanometer. And they do wonderful things. They produce, they replicate, they develop resistance to external stresses. They digest, they reproduce. All this complex machinery exists only in a nanometer size of the cell, 5-6 nanometers. In that, this whole machinery is working, producing, replicating, duplicating, reproducing, developing immunity. All this thing is happening. So can we learn a lesson from this life sciences and biology and modify our living? The first revolution did wonders, and now this nanotechnology revolution will create wonders. The size of a hair, if I pluck a hair, is about 100 nanometers. And the size of DNA in your body is about 2 nanometers. So that means I have to split my hair 50,000 times width-wise in order to get a DNA molecule. That is the level we are talking about, what is nanoscale. So materials behave differently when they go to that scale. Normal macroscopic objects behave differently. They follow classical laws of physics, whereas when you go to a nanoscale, they become quantum behavior, entirely different behavior. Their properties change. Everything changes. Why is small? Small is good. Small is beautiful. It is faster. Don't you believe? There is a dye. The red one is potassium permanganate. Low molar mass. It diffuses faster. Methylene blue dye stays inside. It moves faster. It is lighter. Can get into smaller spaces. It's cheaper. And it's much more energy efficient. In Zurich, IBM, they investigated this wonder molecule called graphene. It is carbon atoms in a hexagonal ring, single atom thick. And they investigated the structure by using atomic force microscopy. The inner bonds are shorter than outer bonds because there are more electrons here. So there is a distortion of this hexagonal ring. This is a wonder molecule, graphene, as you will see. Small is beautiful. You take bulk of gold. Bulk of gold. This is the nanoparticles of gold. You can see when you reach the nanoscale, the melting point decreases rapidly as the particle dimensions reach the nanoscale. Their properties change. There have been nanotechnologists in medieval period. The glass makers have been using gold and silver nanoparticles to create such beautiful glasses. But they did not know that they could change the size and they could change their properties. If they knew, if they could understand the nanoscience, they would have done much more beautiful things. So simply, they put some nanoparticles in glass. They are of different sizes. So as you change the size, their properties change. They absorb at different light. Their optical properties change. Their magnetic properties change. Their morphology changes. Their physical, nanomechanical properties change as you change the size. Not only the size, but also if you change from spherical shaped nanoparticles to prismatic shape, again the color changes, and you mix it with the glass, it creates wonders. Beautiful. Industrial Revolution. Man's progress is marked by such technological breakthroughs. We had Stone Age for a long period, nearly for 2.5 million years. Prehistoric period, when they used stone to make some implements or weapons. Then came the Bronze Age, where copper and its alloy bronze was used. And then we came to Iron Age, which is archaeological period, where the prevalent use of iron was there. And then, of course, we had this 18th century industrial revolution, which changed our lifestyles completely. And now we are in the nano age, where nanotechnology revolution, as you will see in the coming slides, is already happening. Much of this motivating force for nanotechnology has been in the top-down fabrication, where from the integrated circuit industry. So Moore's law, where every few years the size of the transistor keeps on decreasing. So in 2009 it was 15 nanometer. By using some, rather than photolithography, if you choose to do electron lithography, etching, cutting, etc., plasma, and then you can go down to the size of the integrated circuits, the transistors, and then because we want more memory and more processing power. So why properties of the materials change at that scale? Because surface to volume ratio changes. Most of the atoms are in the surface. In the bulk, they are far less. And so most atoms being at the surface rather than the bulk, they are very weakly bonded and they become very reactive. If you take a sheet of aluminum metal, keep on cutting it, it still behaves like aluminum. Till you can see it under a microscope, still it will behave like aluminum, very, very small. But keep on cutting it, when the size reaches about 10 to 20 nanometer, it explodes. There is a talk of using aluminum powder in rockets. So it's just like if you take a cat, keep on shrinking it, and all of a sudden, out of the blues, it turns into a dog. It's that situation. Keep on squeezing the cat, it becomes a dog. So not only that, so because of that change in properties, because bulk disappears, very, very small quantity as compared to the surface becomes very active, their properties change, morphological, material, mechanical, elastic, adhesive, all these properties change when they become so very tiny. Quantum mechanical effects become important. And if, for example, quantum dot, they call it, if the size is less than 10 nanometers, quantum confinement prevails because the size of the particle is of the same dimension as the wavelength of electrons. And so electron is not happy in a small scale, and so the quantum confinement effect occurs, and so it starts following the quantum laws, and by changing the size, etc., we can govern their electronic, optical, at what wavelength it will absorb. That is why the color changes. Magnetic properties we can change by changing the size. This is just to give you an example of different, in the materials, they mix it with a variety of different additives, in other words, blending. So because to improve discharge properties, to improve durability, to improve dispersion of the particles, and so they mix with variety of different things, conductive additives, electronic additives, and so most of the success in building these nanomaterials has been in blending or preparing composite materials. Here's an example that they can coat it with the different nanoparticles, and they can be tailored to specific application. This is the brick of the wall which is sprayed with a nano coating, and this is looking at a very magnified scale. So these things they are using for conducting variety of properties. Here is something for you to relax and get ready for the disco. gives you an idea. There you go to the next one. Hope you enjoyed it. Now, such an ability to coat the surfaces to get different sorts of properties. There you saw only hydrophobic nature, but we can make them resistance, scratch resistance, clothing, variety of, you'll see some examples as we go along. So this is the ability we have to produce and modify these nano-sized materials. It has opened up a diverse range, a myriad variety of applications, as you can see here, in all sorts of industries. It has created an unending stream of applications of this nanotechnology, which reflects the rhythm and dimensions at which the nature operates. Coming from stain-proof, waterproof, wrinkle-resistant clothes. You don't have to iron them anymore. Titanium oxide nanoparticles in sun creams. Zinc oxide sunscreens to save your skin from UV light. Fast-absorbing drugs and nutrients. Food packaging materials. Extra strong tennis rackets, as you can see. And scratch-resistant paints. Self-healing materials, which will heal on their own. All these are commercially already available in the market. We can make things smaller two ways, going top down, where we carve away things like a sculpture. In nanotechnology, they call it lithography techniques. They use photolithography or electron lithography. And so going down, you waste a lot of material, and depends upon the limit of the tools, how small you can go. So these are some of the limitations of going down. But in the integrated circuit industry, in the computing, this is the way they have been using, cutting, etching, grinding by using electron lithography, etc., to create IC circuits, the transistors. Bottom-up approach is building atom by atom, molecule by molecule. It's just like building made from bricks. In nanotechnology terms, they call it self-assembly. Atoms and molecules, you create a structure, different structures, they merge together to create a bigger one. You have much better control. And you can use some catalysts, you can use some fields, electrical fields, magnetic fields, to guide those atoms and molecules to create the structures that you want with the properties you desire. How do you build? How do you image them? How you characterize them? 1986, as I mentioned, this was discovered. Without this technique, atomic force microscopy or scanning probe microscopy, nanotechnology will not exist. And this is first time they used xenon atoms. With each atom, they could put it in position to create this IBM. This is a red blood cell of a human body, is about 6-7 nanometer diameter. And here are some stem cells. When they differentiate into neurocells or muscle cells, you can go to that scale. Here it is 100 by 100 micrometer, this size of this cell. So we can observe things by using these microscopic techniques. These did not exist. And there are other types of scanning probe microscopies which can give some electrical and magnetic property measurements also. These are the pioneers and the greatest spokesmen for nanotechnology. Richard Feynman from Caltech, he gave the concept, he had the vision in 1959, but the word nanotechnology didn't exist. These are the people who discovered their fantastic microscopes that we can go to that level. And that is, this discovery led to the discovery of bulky balls, fullerene balls, carbon-60 in the form of a shape of a football. And Dr. Dexler, he sort of developed and popularized this concept. And it was a Japanese, Dr. Ijima, who in 1991 discovered the carbon nanotubes, and this set the stage for nanotechnology revolution, which is occurring globally. In brief, what happens with this microscope that they discover? There is a tip that scans the surface, laser is focused, gets reflected. When there are undulations on the surface, it converts this signal into an image. Not only an image, but you can measure their properties. And if you use, apply the force more, you can scratch the surface. You can create your own patterns for. This is a surface sensitive instrument. It can image, it can measure the nanomechanical properties, it can measure the interaction forces between different biomolecules, polymers, materials, membranes, DNA, proteins, cell-cell interactions, and then it can sculpt the surfaces if you apply a greater force so that you can etch lines or complex patterns for building electronic circuits, thereby increasing the computer memory on an atomic level. And so initially we knew only two structures. Diamond is said to be the girl's best friend, but now with the discovery of nanotube, probably the girls might change. They might like, at least men would like to give nanotube. It's much cheaper as compared to diamond. So it will be men's favorite, definitely, nanotube as compared to diamond. And then you can create structures like this. This is carbon nanotube, this one here, and this is separating the graphene layer. So now applications, you can see, you can control the length, width, and the separation distance between the graphene layers. And so you can control sort of, you can tune the porosity for hydrogen storage from fuel cell batteries as application in energy. And then you can sort of dope it with some semiconductors for IC circuits, transistors, etc. So you can go to that level. The size is only 1 nanometer. Now those carbon nanotubes that you saw, if you take 1 inch thick of that carbon nanotube, it is 100 times stronger than steel. And it weighs only 1/6 of the weight of steel. Can you imagine building by ropes, not by steel? Or can you imagine elephants dancing on a platform supported by those ropes, carbon nanotube ropes? They are that strong. And naturally it has led to revolution in this industry, because rather than aluminium, they have prepared carbon composite nanotubes into, and so they have created much lighter, and so it improves the strength, integrity, and the fuel economy. And so it has led to this revolution in airspace. Airspace industry. Coming to medicine use, for example, you take gold nanoparticles, you can adjust the size so that it absorbs only infrared radiation or near infrared. And gold particles you coat with antibody to a disease. Say for example, you can take iron chloride, put some water, makes iron hydroxide. Put some caustic soda, it gives iron oxide particles. Iron is magnetic particle, it is positively charged. Now virus antibody has got a negative charge that binds electrostatically. And on the other end of the AIDS virus antibodies, you can have virus, because it is an antibody-antigen interaction. And then magnetic particles are floating with all the virus, AIDS virus accumulated. You can just fish them out. That is how the cure of cancer will be there. It is not only AIDS, it is any, because 99% of the chemotherapy drugs, they do not reach the cancer cells. Already the clinical research has been going on. It has passed 2 stages with animals where they have got 100% results already successful. Third test is due. If it is successful, it will be curing at least about 30 different types of cancer. So that you have gold particles, you coat them with antibodies, and then they go, the virus goes and attaches, and some way you can take them out. Or you can tune the size of those gold nanoparticles that they absorb only infrared. If the infrared radiation you shine through your body, skin remains unaffected. It only goes there where the cancer cells, because of the tumor, there are some, those nano shells, they call them. They're so tiny they can go into the capillaries and sort of form a sphere around the tumor. And then you shine infrared. Infrared is absorbed by those gold particles, and that heat is conveyed to the tumor particles. Those cells die without harming the normal cells. And this research also is going on extensively these days on cancer. Artery cleaning is here as another example. So these are some of the applications on the medical side. In construction, silica is present in the normal mix, but if you take in the cement, if you take nano cement and you put nanosilica, nanoparticles of silica, their properties change. The micro and nanoscopic structures make them so strong, they improved mechanical properties. So they are using nanosilica cement, much improved properties. Steel, copper nanoparticles you put, it improves the imperfections. Fatigue is gone because of those number of voltage enhancers that are present. They can cause fatigue and the material failure. And so they can prepare such composites with copper, with steel. It is giving fantastic results. Here is a nano fridge. It's available in the market. You can search for nano fridge. You'll find this one. And it is coated with silver ion nanoparticles to kill bacteria and fungi. In the paints, you already discussed, you can have sort of self-healing properties, insulation, protection against corrosion, hydrophobic coatings, variety of different things one can get commercially these days. Coming to nanoparticles, these are silver nanoparticles, gold nanoparticles, in liquid, copper nanoparticles. You can see the changing the size. This is here a semiconductor, cadmium selenium. It is used in biological nanoparticle fluorescence. Dyes are being used these days, and it is used in computing industry to create these quantum dots. We call them quantum dot nanoparticles. Cadmium selenium, as you change the size going from left to right, the color changes. If you observe in UV light, it is different color. In visible light, it is different color. You can change the properties altogether, optical properties, magnetic properties. And so gold nanoparticles here, they are used. These different colors can be used in paintings to change the color of the paintings, and in biomedical science and in computing. This is all the applications of nanotechnology. Here is something more for you to relax for some time. Flexible display screens. That's enough. So microprocessors, before we go here, you'll see Lady Gaga soon. Before we go there, microprocessors less than 100 nanometer size. The smaller the size, the more processing power, the more memory you can store. Nano dots we talked about, the memory increases. Still we have yet to see the increase in the memory by using those nano dots, and quantum computers still will be coming on the market. Now coming to food, nano food. Food, people talk about gray goo, but all these foods already contain nanoparticles. They are already in our plates. Titanium oxide, thin layer, 10 to 50 nanometer is deposited to protect them against absorption by air or moisture, to protect the food. It is already there in our plates. Do you think by adding more, we'll be killing ourselves? We can smuggle vitamins into our body by putting those artificial nanoparticles. But naturally, of course, I'll discuss the ethical and environmental health and safety issues later on. But what I wish to say here is that the nanoparticles are already there in our plates. Here is a filter, nanoscale filter, powered by solar energy, and it can clear all the drinks, milk, from bacteria, Listeria, all the nanoparticles it can clear. Nano capsules, they can give you food supply when you are hungry. They will keep you fit and tight forever. Nano food, they will release food when and you require them. The Listeria, bacteria in the milk, again the same function that you have magnetic ion oxide particle with the antibodies, and so the virus binds to it, and these magnetic oxide particles, they can be fished out. And then there is a indicator enzyme also is tagged onto this microsphere, the nanoparticle, which changes the color of molecule, tells you that Listeria has come out of the milk. So here is, okay, so handheld instruments are also available based on the similar principles, spinach, etc. So you can detect whether there is, and you can take out those bacteria, germs, etc. using these nanoparticles, same nanoparticles. You can functionalize them. Here is a bottle. The bottles that you find these days in which you drink, they are not plastics. Plastics, there is a problem, it can absorb air, it can absorb moisture. So we want to increase the barrier capacity. And so this is 100 times stronger plastic you can make with all the barriers and keeping food longer. Drinks fizzier. So clay is used. Nanoparticles of clay are embedded inside the plastic, and it improves the properties of this plastic. Lady Gaga, 2010 MTV Music Video Award. What is she wearing? Beautiful dress. But how is she going to store it? Nanotechnology has a solution. So with the nano clay or composite nano clays, we mix with plastic. But plastic, polyethylene or polypropylene, they use it. But if we use biodegradable polymer, polylactic acid, for example, we form with a clay and store her dress, so we can look after her biodegradable wardrobe very well using nanotechnology. Fantastic, isn't it? For the poor, sustainable water. So you have nanopores, only pure water comes out. Bacteria, it removes all the heavy metals if you use magnetic nanoparticles, nanomembranes, the nanoshells, nanorods, nanofunnels also I will talk about. So everything is nano. The clean water is scarce in developing world. So especially for the astronauts, if you take a pint of clean water, if you want to ship it to the space shuttle, which is about 250 miles from here, a pint of clean water will cost about 12,000 pounds. But using these nanoporous materials, urine will be recycled of the astronauts, so that you don't have to send 12,000 pounds worth of 1 pint of water, clean water. It will come out clean out of those nanopores. Going further, sustainable energy and environment. Fantastic. Here I'll give you an example. These are the solar panels people used to use. I mean, we use fuel cells, petrol, gas, nuclear power, biofuels, everything leaves waste. Solar energy is renewable, does not leave no waste at all. And so can we use solar energy to solve the world's energy crisis? Yes. So these solar panels are there. If they are fitted with nano rods, the light comes out at all the angles. Otherwise, they absorb only 67, the old panels, they absorb only 67% of sun's light. But if you use these, embed them with nano rods, they can take 96.5% of sun's energy. The efficiency increases by using nano rods. And now, there are three things. One is production, harnessing the energy. Second is transporting all over the world through the electrical grid. At the moment, it consists of copper and aluminum wires, where most of it is lost as resistance, as heat. The third thing is 20% of the electricity we use for lighting. And if we can use, again, nanotechnology based bulbs, it will provide solve the world's energy problems. Now they have come with paint. Paint is encapsulated with nano funnels, so that they absorb light at the funnel on the top, and then the angle becomes narrow and narrow till the light is focused on the most active point on the solar panel. So they have developed such paint with the nano funnels. And so they create 1 mile of sheet on a plastic sheet. They can paint it 50,000 cells, solar cells. And now they have coated it on a plastic sheet which is transparent. You can put on the windows of the car, windows of the offices. You can see, but it will be collecting electricity all the time. It will be saving the solar energy. And that solar energy comes, you connect it to a fuel cell. Fuel cell, when it's daylight, it works in reverse. The excess energy that you don't use is converted to hydrogen. Hydrogen storage, I told you before, once I built that building structure, you can store hydrogen by tuning the porosity, and you can store it. When the night falls, they work normally. Hydrogen is changed back into energy. We can improve the efficiency of fuel cells by using nanotechniques, nanomembranes. They have already found the efficiency has increased enormously. Rather than using metal electrodes, now they're using nanotubes. It has increased the efficiency. For transportation, rather than using these copper and aluminum wires, if you use 1 million of those nano wires of carbon nanotube, they are no heat, no energy loss. 100% energy, you can send it all over the globe using those carbon nanotubes rather than copper and aluminum. So it will amount to rewiring the whole of the globe. Here is a battery which is less than the thickness of a paper, and it is 10 to 20% more brighter, more powerful. And you can recharge 90% in 15 minutes. Less than the thickness of a paper. For MEMS, David Bradley is here, his favorite MEMS. It will change into NEMS, electromechanical devices. So here they coated silicon with lead magnesium niobate, lead titanate. And they found a giant piezoelectric effect. Some of you may not know what is a piezoelectric effect. It is change of mechanical energy into electrical energy or electrical energy into mechanical energy. Like you go to disco, the music you're playing on the guitar, mechanical energy you're applying, it is changing into electrical energy. Or a lighter, you apply the pressure, spark is there. It converts into voltage. And so, piezoelectric materials. Clothing, electronics, the clothes, you can sort of put some electronic circuits so that it can take care of your health also what you are wearing. It can control the temperature. Military, police people, they can change the color, the shape. The color can change for hiding, for the military purpose. Already these things are happening now these days. Nanoelectronics, you use nanowires to connect different components of the electronic components. The same nanowires can be put into the human body through a catheter, and the pulses can be given to the brains. Neuropulses can be monitored so that they can cure diseases, neurodiseases such as Parkinson. Already this work I heard in the news yesterday. You heard too. Already this work is being done. So I think, in conclusion, all those techniques, microscopic these techniques, especially without them nanotechnology won't exist. Nanoparticles, carbon nanotubes, they are the most used tools in nanotech. You can move atoms around, you can nanofabricate, you can nanoscalpel, you can do nanosurgery. And so these days some hyphenated techniques are also in use. Here is some of our own, how our work fits, and especially for forensic science people here. These are some sticky tapes used in crimes for rape cases, for hiding contraband goods or documents. So 3 different tapes, we could sort of distinguish them for taking from the lab to the court to prove what is the origin of these tapes that were used, recovered from the crime scene with the identifiable source. With their mechanical properties are different, their morphological properties are different. Same way in fingerprints, the secretions are amino acids. If we take these gold particles and we attach anti-amino acid antibodies, they can attach to the amino acids on the fingerprints and they glow like in a starry night, they glow in the dark. The weak fingerprints, those are not visible, they are on tough surfaces. You can use these nanoforensics is coming up. It's not only that, there are plenty of more examples. DNA they want to put on a microfluidic chips, lab on a chip, because DNA analysis, extraction, amplification, etc. If all those things can be combined and integrated on a single chip, the whole DNA, by the time you're in the police station, the DNA will be searched in the database. All that lab on a chip will do the job, and before you go home, either you're clear or this is your DNA. That is the way nanoforensics is going to move. Veterinary medicine has a hybrid field. Again, this is hybrid discipline which is applied to animal nutrition, animal health, animal disease diagnosis, and targeted drug delivery, just as in the case of human beings. Same thing can be done for animals also. Nanomedicine, Professor Andrew is here with us from St. Andrews Medical School, and so with St. Andrews we did some bladder cancer cells and normal bladder cells. We could distinguish them with the high specificity and sensitivity, because it is essential that they should, for any disease diagnosis, we got to have high specificity and sensitivity. We should be able to screen 2 types of cancer cells, cancer and normal cells. They are different. Red one is cancer cells, the blue ones are normal cells. By again applying the same nanotechniques, atomic force microscopy, in this case we combine with Raman spectroscopy to find out in cancer cells whether DNA is more, proteins are more, etc. So this is already published. with the St. Andrews Group. And these colleagues in James Hutton Institute, Michael Teliansky and Andrew Love is here. They are using virus particles from plants to make nanoparticles. And those nanoparticles they made from bovine virus. Bovine, for me the name pronunciation is so difficult. Bovine papilloma virus. And so that is this BVP stands for. And so they make virus-like nanoparticles. This size is 50 nanometers only. And then they decorate with some peptides, functional peptides, so as to make some vaccines and diagnostic kits. So this work has been done in collaboration with the Modern Research Institute, which is a huge institute for animal research, animal welfare in Edinburgh. And we want to use the same thing. We want to use tobacco mosaic virus and coat it with some metallic bonding particles, nanoparticles. And so we want to tie calcium, which we require for bone repair. And that work is under planning. So that's the nanotechnology. Just to give you something, how much investment has been there. US alone in 2001 to 2004, 20 billion. Out of this for health and safety, 750 million, lot of investment. Corporations, they will invest only in 2014 alone, $4 billion. And the estimate in 2015 is, three different estimates are there between 1 trillion to 3.1 trillion. So that is the estimate, trillions. Estimated growth in drug delivery and drug diagnostic is of this range. By 2001 it will go to. So as you have seen that all these business executives to venture capitalists, those who want you to invest the money in the nanotechnology industry, they think that nanotechnology in combination with IT, biotech, which will be called nanobiotech, and cognitive sciences can lead to all the revolutionary advances in variety of different industries, no matter how far these nanotechnology applications, from brighter bulbs that use less electricity, high capacity batteries that can be charged in no time, 100%, to targeted drug delivery that will reach the body parts where you need, when you need it. How far these nanotechnology applications will go, but soon they will be with us. We cannot live without them. They will be with us as common and as vital as a piece of sliced bread in the morning. And there is something more. The electrical grid I talked about, so I'll just give you that example. This is the Nobel laureate who discovered it. After 3 years, poor chap died of a cancer. He said if he could live for 20 years, he was definite that his cancer will be cured by using nanotechnology. So it was sad, but he said if Mother Nature allows us, we will restring the whole electrical grid throughout the world, saving energy using nanotechnology, solar energy alone. Just 2 slides more before I finish. Environmental health and safety, ethical, legal, and societal issues, they are much fundamental. And so case-by-case study has to be done at a deeper level, and whether the nanoparticles, how they interact with humans, animals, plants, and the environment, whether they stay there, and so whether they accumulate undetected in water or in food chains, whether they can continue and can cause damage. Such safety issues are the key issues because nanotechnology tsunami is moving. When it reaches the shore, it moves at a longer wavelength, low waves, but when it reaches the shore, there is no time. So we are already into this revolution. And so here is my own thoughts, a thought for you too. We and our mothers. My nephew, he sent me this picture. I thought I could fit into this lecture. And our mother nature and we are all connected. Our mother kept us in her womb for 9 months, going through excruciating pain, and left us to venture into the outside world to explore on our own. We cannot devalue her worth. Same way, Mother Nature looks after us so well, provides us all the amenities and immunities against diseases, and then leaves us alone to venture and use the nature's resources for our benefit. So how can we forget nature? So we have to work in harmony, keeping nature to solve the world's problems. So we have to duly consider environmental health and safety issues, ethical, legal, and societal issues, educational, workforce. Workforce in one sector will decrease, people will go out of jobs, but in other sectors it will come up. So one has to think positively. Nanotechnology is trying to decipher nature's tricks, but nature is still the king. We can't live without that. And thank you very much for your patience. You have been a very good audience.
It's my happy task as principal now to give a vote of thanks. In fact, 2 votes of thanks. Firstly to you, Ashok, for a fascinating and entertaining talk. Secondly, thanks to all of you, to the audience. I notice I'm copying Ashok. It's always difficult when you follow somebody with a fantastic talk. You never know quite what they're going to say. So let me add my thanks. Ashok is here as a professor. He is professing his subject. He's professing his subject within the Abertay community, and he's professing his subject from the Abertay community to the wider community in Dundee and beyond. And that's, for me as principal of the university, a very important aspect of it, part of our engagement with the wider community. So let me add my thanks to Ashok's, to all of you for coming. So thank you very much for coming.